Now for cutoff wavelength, single mode operation only occurs above the threshold cutoff wavelength of lambda c, that is 2 pi an1 by vc into root over of square root of 2 delta. So vc is the cutoff normalized frequency. The same fiber we can obtain the inverse relationship like lambda c by lambda equal to v by vc. When vc equal to 2.405, it becomes v lambda by 2.405. Let us have a numerical problem. Determine the cutoff wavelength of for a step index fiber to exhibit single mode operation when the core refractive index and the radius are 1.46 and 4.5 micrometer respectively, with the relative index difference being 0.25%. So lambda c equal to 2 pi an1 root over of 2 delta by 2.405. Putting the value, you will get 1214 nanometer. So this is the cutoff wavelength for this particular fiber. Mode field diameter and spot size. So inside the fiber, we may have this type of electric field distribution. Okay, this type of electric field distribution. The mode field diameter is an important parameter for characterizing single mode fiber properties, which takes into account the wavelength dependent field penetration into the fiber cladding. That means it will give us the idea how much power is going through the cladding. In this context, it is better measured to the measure of the functional properties of single mode fiber than the core diameter. For step index and graded index, or that is the near parabolic profile, single mode fiber operation near the cutoff wavelength of lambda c, the field is well approximated by Gaussian distribution shown here. So in this case, MFD is generally taken as the distance between the opposite 1 by E, that is 0.37 field amplitude points. So this is the E0 and this is E0 by E. Okay, that is 37% of E0 field amplitude points, and the power of 1 by E square, that is 0.135 points in relation to the corresponding values on the fiber axis, that is shown right here. So from E0, here we have E0 by E, here we have E0 by E. So this distance is omega 0. So MFD, that is mode field diameter, is twice omega 0. Okay, assuming the profile is Gaussian in shape. So another parameter which is directly related to MFD is the spot size or mode field radius omega 0. So MFD equal to 2 omega 0. Omega 0 is the nominal half width of the input excitation. The MFD can therefore be regarded as the single mode analog of the fiber core diameter in multimode fibers. However, for many refractive index profile and at typical operating wavelengths, the MFD is slightly larger than the single mode fiber core diameter. Effective refractive index. It is convenient to define an effective refractive index for single mode fiber, sometimes referred to as the phase index or normalized phase changed coefficient, that is N effective, by the ratio of the propagation coefficient of the fundamental mode to that of the vacuum propagation constant, that is NF and effective equal to beta by K. So group delay and mode delay factors, the transit time or the group delay tau s for the light pulse propagating along a unit length of fiber is the inverse of the group velocity Vg. So tau g equal to 1 by Vg, that is d beta by d omega, that is 1 by c into d beta by dk, and we already have this relation. So 1 by c into ng2 plus n2 delta dvb by dv. The second term, this one result from the waveguiding properties of the fiber only, and it is determined by the mode delay factor dvb by dv, which describes the change in group delay caused by the change in the power distribution between the fiber core and cladding. So mode delay factor is a further universal parameter which plays a major part in the theory of single mode fibers.